science department, and now he works in 3 different fields, including near-term algorithms, quantum cryptography, but non-QKD, and quantum benchmarking, or benchmarking of quantum systems. And actually, when I did my master's thesis, he was my advisor, and we exactly worked in quantum benchmarking, in randomized benchmarking. That's partially the reason that I'm here, so yeah. I'm happy that he's now here giving the talk, so yeah, I hope you all enjoy.
Hi, thanks for the introduction, and thanks for the invitation to give this lecture. So this lecture, I eventually decided, so the title was Quantum Algorithms and Quantum Complexity, so now it's Quantum Complex Theory and Implications. I thought that having a proper introduction of quantum algorithms and complex theory would be, a bit too much for one session. Okay, so I'll start with the overview of what I'm going to cover. First, I'm going to give some motivation of and definition of complex class, and before going to the different complex classes and so on, I'll define the different models of quantum computation. Some of you are familiar with all or some of those models, and these are useful things to understand exactly what's the effect of complex theoretic results on the capabilities of different models of computation. Then I'll introduce some complex theory, some basic complex theory, and the classical complex theory classes. So this is a detour, but it's essential background. And then I'll introduce the main quantum complex classes and the implication that this relation and results in complexity in quantum complex classes have for classical emulation of quantum systems and the quantum computational advantage and generally about achieving speed up. Here, notice that some of the pictures from the slides are taken from Andrew Georgiou. Actually, was my former PhD student, and now I think he's postdoc at well, I don't think he's postdoc at ETH. Yeah, so thank him for that. Yes, so I'll start with the motivation for this. So the first thing is that complex theory helps us to understand what we can and we cannot do efficiently. And this applies to classical algorithms and quantum algorithms as well. It also gives us some insight about the power and the relative power of different models of computation, whether you can, do certain things equally well in these different models of computation. Third, now looking from the problem, so if you have a particular problem, it gives us complex theory insight on the hardness. So even if you can do something efficiently, the question of how efficiently or the question of how not efficiently you can do something, that's something that complex theory can help you understand. And finally, of course, there are some applications of complex theory and the implications of complex theory. One prominent example is in cryptography. I'm going to mention some things about this. But classically, even the existence of the concept of public key cryptography relies on certain assumptions about complexity classes. Yeah. So what is, so I hope that if some of this doesn't sound familiar, it will become as the talk progresses. But if you have some question that cannot wait or you think it obstructs you from understanding things, please don't hesitate to stop me and ask. So computational complexity is a classification of problems according to their difficulty. Now, what do we mean difficulty? We measure the amount of resources that one needs. So in order to perform a computation, you need time, you need space, or you need number of gates, and so on. And the way you quantify this is how it scales with respect to the input size. So if you have, your problem can have different instances of a problem. So factoring 21 is easy, but still has the same complexity as factoring a very large number, because we are talking about the relation of the input, in this case 21, with the process of factoring 21 and so on with different things. So we quantify the relation of input size with difficulty of the problem. And that's important, for example, for scaling up things, but if for some reason you are particularly interested of a problem that has fixed size, this may not be the most relevant quantity, because you may be interested for this fixed n, what is my quickest algorithm? And my quickest algorithm can be something that doesn't scale well as you go to larger sizes. So these two are always hand in hand, but it's good to keep this in mind. So what a complex class is is a classification of set of problems that have a related resource-based complexity, so that they require similar type of resources. And I'm going to define the complex class, and you'll see what this is meant later on. But before I'm going there, I'm going to define the different models of computation, in particular different models of quantum computation, because that's what we are interested here. So before going to the complex classes, I'll do this detour for a while. So the models of quantum computation, there are many more, well, not many, but there are a few more models of quantum computation, but I'll focus in those. So the first one is the one that everyone knows. I'm sure if you're in this room, you should definitely know that one, is the circuit model. And there is the direct quantum analog of a classical circuit computation. And then there are two other models of computation that don't have classical analog, which is the measurement-based quantum MBQC, and the adiabatic quantum computing. So these two are two models of computation that have no classical analog. And then there exists a heuristic algorithms, one of which is the class of hybrid classical quantum algorithms that I'm sure you have heard, even if you haven't worked on them. These days it's a very trendy and nice topic, but also very trendy. So models 1 to 3 are what are called universal, and you'll understand what universal means when we define complexity. Well, universal basically means that you can do any quantum computation using those, but what you mean you can do, it's also subject on how efficiently you can do this. So anyway, they are equivalent complexity-wise. But model 4 and some restricted versions of the first 3 models are not equivalent complexity-wise, so they're not universal. They're not as powerful as the other models, but they're suitable for near-term devices. So in that sense, particularly these days, we are interested in those models as well. So I'm going to say a few words about them as well. OK, so let's, for warm-up, I start with a circuit model that you know, and we'll go through this. I'm not going to give details. This is just high-level picture. So the basic mechanism is that one has an input, and then unitarily you involve with input through a quantum circuit, and we apply the gates one by one. And then at the end, we have a measurement to extract some classical information, essentially. And the resource cost in this is the number of gates. That's the main resource that we count, how many gates you need. Of course, there are other things like what is the depth of the computation, and you can, practically, this is an important aspect, and you can even define a set of problems that can be solved by a circuit model that has, let's say, constant depth or logarithmic depth, and that's a different restricted complexity class. But anyway, I'm not going to get into those details. So just high level, it's the number of gates that we count here as our cost. The measurement-based quantum computing is also known as one-way quantum computer. This is probably the thing that few of you are familiar. So how many of you have heard MBQC? Ah, good. I actually thought there would be fewer, but yeah, that's good. OK, so then the basic mechanism. So this is a model of computation that you start with a large entangled state. I mean, which is generic, so it doesn't depend on the computation you want to perform. So, and let's say it's a 2-dimensional lattice of, you have these qubits, and you just do control Z between, any neighboring qubits, let's say. And then to perform the computation, what you do is that you do single qubit measurements one by one. So you measure this. And then measuring one layer of those, what it does is that it teleports the state that you started in this next layer. So you can see that. Okay, let me use that. Okay, so basically it teleports, once you measure single qubits, all this first layer, what you do is that the quantum state that you started here has been teleported here with a gate applied to this. So the idea is the gate teleportation. So you do teleportation, but you also teleport and do a gate on top of it. Right, so you can do this, and then the next layer, next layer, and next layer. So each layer is like you apply a number of gates in your teleported quantum state, roughly speaking. And then the resource that you have is how much entanglement you consume. By the way, so this grid, it doesn't need to be prepared in the initial moment of time. So by looking at this, people say, oh, this is horribly impractical. We will never be able to do that. But this is not quite the case, because I mean, if you know the details, you basically need to prepare these 3 layers. And when you measure this, then you can entangle the 4th layer and so on. So you can actively be preparing this state. So it's not like you really need all this big entangled state. And this type of model is for certain hardware, it may be better, easier to implement. So for example, for certain photonic quantum computing architectures, MBQC is the preferred way. And there are some applications also that are easier done in MBQC. And of course, there's a question, is it equivalent with the circuit model? Yes, it is, in the complexity theoretic sense that I have not yet defined, so it does make sense for me to make this statement, but yeah, you should post-select after my explanation to what happened there. Anyway, so the resource here is how much entanglement you waste, you consume, basically. Okay? So then the next model of computation of universal is the adiabatic. So how many of you are familiar with adiabatic quantum computing? Okay, yeah, similar with MBQC. Okay, so here the main problem, the basic, so the starting point is that you take whatever problem you want to solve, and you find a Hamiltonian, that the ground state of the Hamiltonian essentially gives you the solution to the problem you want to solve. We're going to see this more later. So this is the so-called K-local Hamiltonian problem. I'm going to say more things about this later, but for now you just believe me that this can be done. You can turn your problem to this type of finding the ground state of Hamiltonian. And let's say that H1 is that Hamiltonian, your problem Hamiltonian, the one you want to find the ground state, right? Then H0 is a different Hamiltonian that you know the ground state of this Hamiltonian. And not only you know the ground state of this Hamiltonian, but it's very easy to prepare. So for example, it can be the Hamiltonian that the ground state is just all plus states. So if you take tensor product of x's, or you know, some very simple Hamiltonian that you can easily locally prepare the ground state of it. Okay, and then you construct this time-dependent Hamiltonian, which runs from T0. Well, I said T0 equals 0 in this expression anyway. So from T0, which is 0, till Tf, which is the final time. And what you do is your time, this Hamiltonian is time evolved. At time t equals 0, this is H0 and this is 0. So you start with H0. And as you evolve from t equals 0 to t final, this term reduces and this term increases. And then at the end, you are left with this Hamiltonian, right? Now, if you evolve your system with this time-dependent Hamiltonian, and you initiate it in the ground state of your initial Hamiltonian, if you do it really slowly, what you do is that you constantly remain in the ground state, because okay, you start in this ground state, you deform the Hamiltonian, so it deforms like this, and it doesn't jump from the ground state if you do it slowly enough, so you end up with the ground state of the final solution, and then you measure the end, and then you get your desired solution, okay? And now, for this to work, you need to be able to, so if you see this, if I pull it up rapidly, this may bounce, for example, very rapidly speaking. This is not what happens. I can explain exactly what happens. But the point is that you need to do it slowly in order to remain always in the ground state. And the cost of the adiabatic quantum computation is how slow I need to evolve the system to ensure adiabatic evolution. Adiabatic evolution is that I remain always in the ground state of this time-evolved Hamiltonian. Is this clear? Yeah? Any questions? Okay. So that's adiabatic quantum computing for you. It's this, and it's also a universal module of computation. Now, there exists, before I go to next, there exists a heuristic version of adiabatic quantum computing, which is quantum annealing, is basically what D-Wave, I mean, I'm sure you've heard of D-Wave, it's what they're using, which is not exactly the adiabatic quantum computing, actually. There are some differences, okay? So the difference, well, the first point is exactly the same. So you do the same mapping that you did for adiabatic quantum computing. But now, instead of using the concept of adiabaticity of the evolution, you use the concept of tunneling. So basically what you do is that you don't start from the ground state of anything. You start somewhere, which you evolve it under Hamiltonian that at the end of the evolution will be at the correct ground state, and evolve it in a way that you cool it down, okay? And essentially, you turn off some external field, and you cool it down, and you hope that you'll end up with a solution being at the ground state. And the property that is justifying this assumption is this tunneling, because if you have walls, you know, even if they're high, if they're not too thick, then you can tunnel through the wall and reach a minimum. So there exists a classical optimization technique called simulated annealing that has a similar concept, but there you don't have tunneling. So that's why this type of algorithm is better than simulated annealing. Of course, the question whether it's better than other classical approaches, and it's not. It's almost an open, well, I think it's open-ish problem. So yes. The other thing is that this type of algorithm, for specific hardware, for example, for D-Wave, it has fixed connectivity. So to actually do this mapping is not trivial because the connectivity that you have in your device is fixed. So you need to tailor somehow the problem in fitting this connectivity. So you need to embed it correctly. And this is a problem on its own, with some extra computational cost. And it will also require extra qubits. So this is the kind cuts. Now, in this case, the cost, in a sense, is fixed because you can choose how slowly you do this evolution. And you know, the number of qubits you have are fixed and so on. But what it varies is the probability of success. So depending on your problem, you may have high probability of getting to the ground state or very low or even negligible. So that's what really. And this is true with most heuristic algorithms, essentially, because these heuristic algorithms are algorithms that you want to run practically, so even classical heuristics. So you want to run them in polynomial time. But of course, there is a trade-off. You don't have a guarantee that you'll find the solution. And the trade-off, I mean, how likely you are to find the solution is kind of how good your heuristics is. So that's kind of the trade-off here. Is this clear? Yeah. OK. So now I'm going to the other hybrid classical quantum algorithms. So there are things like variational quantum eigensolver, quantum approximate optimization algorithm, and so on. Again, there is no clear picture of the exact speed up, so there are no very clear-cut, complex theoretic results saying that it can offer you advantage then or not. And this is not fault of the field, because it's designed to be a heuristic. The same way that you have, you know, NP solvers for classical problems. Well, I haven't defined what NP is, but assuming that most of you have an idea of what it is. So you have solvers that try to solve problems not solve efficiently, and in many instances, they succeed to solve them, or they succeed to find a good enough solution. And this is what you actually do in everyday life in many tasks that have exponential cost to solve them exactly. So this is a similar analogy. But for those heuristic algorithms, you don't have so well-defined notion of when they are successful and when they're not. You basically need to try and see. And because we don't have large enough systems to play at the region that we may get improvement, this is still kind of conjecture. We don't have a very good feeling how well they would perform. We have some theoretical results, but not in all the cases. The idea is that these algorithms can run without error correction, and this is important for near-term devices. And the idea is that you delegate, high level, you delegate some of the harness of your computation to a classical device in a sense. So you have a quantum device that performs just a small specific fixed subroutine that we hope that our near-term devices are quite good at doing, preparing a type of quantum states. And then you get some input from this, you run some classical algorithm, and then you feed back and you run again a different type of this quantum circuit. So here is basically you prepare a quantum state which depends on these parameters. This is a parameterized quantum circuit. You measure the energy, and then using this energy, you assign a cost on the configuration psi theta, and then you do classical optimization algorithm to try to find the smallest theta. So basically what you try to find is which of choice of parameters theta gives you the smallest energy, basically, and that is your best approximation of the ground state, roughly speaking. And most of these algorithms are, again, based on this Hamiltonian approach. So you turn your problem to the ground state of a Hamiltonian. That's again, the step one of your protocol. Right, and here the cost, the cost can be, so if you tell me that I can do this type of circuits, you basically choose what circuits you're doing. Now, the quality of your result will depend on what type of quantum states you're preparing. This is the so-called ansatz family. But at the end of the day, you can an ansatz family that your device can do with high fidelity, and then see, is this sufficient to give me a high probability of success in this problem or not? So you can, it has a similar flavor with what I said about quantum annealing, that you can basically run it with whatever device you have. It's just that the probability of success will go bad. So yeah. Okay, so that's that. Okay, so let me hijack here and advertise my work as well. This is the only part I'm advertising my work here. It's very recent work. So you can have, so there are many other approaches. So this picture I saw is the central picture for VQE, and there are many optimized approaches, and there are really a lot of research. Some of this was in the posters as well. So, but here I'm just mentioning a paper we had last week, basically. So in VQE, what you do is that you prepare those states, and then you measure the energy, and then you do an optimization here, a classical optimization. Now, one of the big problems in variational algorithms is that this optimization is hard. So the classical problem is hard. So if you choose many thetas, forget about noise for now. Okay, so let's say that we have perfect devices. Still, you need many thetas because you want your quantum states to span the whole Hilbert space, because you want to have guarantee that there is one of your quantum states that you prepare is close to the true ground state, okay? But if you do many thetas, then your parameter space is huge, and the classical optimization runs to problems like you cannot find the solution. You have very small gradients. This is so-called barren plateaus, if you heard. So basically, there are problems that even in the noiseless case, the classical optimization might not be able to give you very high quality of solution. Okay. So basically, the idea we had here is that, okay, let's do a hybrid algorithm that has the same type of quantum states, but instead of actually computing the, do an optimization, instead do a different classical algorithm. And this classical algorithm was basically how small, if you perturb your Hamiltonian just by a bit, how much you need to shift the parameters that minimize your ground state. And so you prepare the state, you make some measurements, then we derive this set of equations, and then with this set of equations, we deduce a good guess of how much we need to change the ground state that we started, so how the small perturbation in Hamiltonian results in a small perturbation in the parameter space. And then you do this again and again, the same way that you do adiabatic quantum computing, basically. So this is kind of a different way. And the basic idea, our hope is that because this thing you can solve efficiently, is essentially a constrained system of linear equations, basically. And this doesn't have the same problem with classical optimization, so we hope that this might evade some of those problems. Anyway, this is the only time in this talk is a lecture, like introducing things. That's the only part I put some advertisement to myself, so right. Sorry for that. Okay, so this is about models of quantum computation. So this was the detour that will make some of the things I'm saying later on to make more sense. So now I'm going back to some background for complexity before I introduce the complexity classes. So there are different sets of problems that one considers. The ones that I'm going to focus is the so-called decision problems. So these are problems that have a yes-no answer. So for example, one asks, is X a prime number, yes or no? Or does X have a prime factor that is less than 50? So things like this. Then there are search problems. For example, find the shortest vector in a lattice. Or find a factor of a number. In many cases, you can, with polynomial overhead, you can turn a search problem to a decision problem. But not always. So for example, for factoring, you can reduce the factoring, which is a search problem essentially. You want to find the factor of this large number. You can reduce it to a decision problem because you can ask, is there a factor below 50? Yes or no? If yes, well, you can brute force that part. If no, then you say, okay, is there a, so you can break down and you can do binary search, and then you can find the. So you can basically do the factoring as a decision problem. And then there are the sampling problems. So assume that we have a machine that gives us samples from a given probability distribution. Can we construct a device that gives us samples from that probability distribution? Of course, in the case that the probability distribution doesn't have a closed form, or well, that you can efficiently describe. And actually, quantum advantage experiments are all that have succeeded or are close to succeeding are all these type of problems, are sampling problems. So this is why I'm mentioning them. Some further notation, well, not notation, and caution. So when I say logarithmic, polynomial, or exponential cost of something, these are the corresponding resources scale as logarithmic, polynomial, or exponential with respect to the input size. Everything is with respect to the input size. And the final comment, you've been warned by the previous lecture. So the previous lecture said, don't trust computer science computer scientists when they say efficient, you know. They mean different thing what everyday people mean. So efficient, to my language, computer science language, means that can be solved at most in polynomial time. And this is irrespective of what? So let's say that you have two problems. I have a problem that, actually this is a true story. I mean, we had an actual such a protocol that scales with n to the 8,000. Okay, I can efficiently solve this problem, n to the 8,000, because it's polynomial. Conversely, if you have a problem that goes like n to the 2 to the 0.00001 n, oh, this is absolutely not efficiently solved because it's exponential. So, I mean, yes, this is the what's it called, the terminology. Of course, it's important to know the concrete cost for specific problems, but it's good to keep this in mind. One of the reasons that people in computer science did this is, well, first that they're strange people, we are strange people, but second is that there is a reason. So in many cases, when you have a polynomial, you can find later on improvements on that polynomial, and sometimes can be really impressive, the improvements. So for example, this protocol that I told you that someone proved that complex class is equivalent with some other complex class because there was an efficient algorithm. By efficient, I mean n to the 8,000. Well, in less than 5 years, there was an n log n algorithm for the same problem. So that's just to give you an understanding. And when we had we brought it down to 2,000. We were happy, yes. Yeah. Anyway, so yes, so you have been warned about that. Okay, so now we start with the decision. Okay, no, this was just to scare you. I'm not going to go to all this. I see I did succeed in scaring you. But anyway, so this is, I mean, and it's a subset of the complex classes. And just even going through what each of those names mean, it will take quite some time. So I'm not going to do this. So what I'm going to do is focus on few complex classes, classical and quantum, very few, that are the most relevant for you. You can ask me about other things. There will be some complex classes that even myself don't know, but yeah, and yeah.
There is complexity too, actually.
Yes, there is, absolutely, yes. There is a complexity zoo that has this, so that's for you, yeah. That's where I go when I don't know an acronym, yeah. So there is a complexity zoo, yeah. Yeah, there are many zoos. Yes, I didn't know about the error correction zoo. It was very interesting to find out earlier. Yeah, and there's a quantum algorithm zoo. I think there's a quantum protocol zoo as well. So, yeah. Okay, so after scaring you, I'm just going to very basic things. Okay, so now I'm going to the complex class P. Okay, so just starting very simple. So complex class P is problems that are solved in polynomial time on a classical deterministic computer. So there are things like you're given a directed graph and you want to find the shortest path, or you're given some numbers and you want to unsorted and you want to sort them, or to invert a matrix and so on. So these are things that you can do efficiently. Well, you can do in polynomial time using a deterministic classical computer. So the idea is that you have an input x. Imagine that is a bit string. And then what you do is that you take this bit string and you do some action to this. You can think of as a gate, or if you wish, or some action. And this takes you in another bit string, another bit string, another bit string. And the number of steps you have is a polynomial with respect to the size of the bit string, of the input bit string. Right. And then at the end, because we are talking about decision problems, so these are decision problems, at the very end, you get an output that, yes, x satisfies this property that we are testing, or no, x doesn't satisfy the property that we're testing. Okay, so this is the picture. Is this clear? Okay. So now I'm going to the next complex class, which is slightly, maybe, probably you have heard of that, but how many of you have heard of BPP? Most of you. Okay, so BPP is the bounded error probabilistic polynomial time. This is what BPP stands for. And it's basically what a classical probabilistic computer can solve efficiently. Okay? So now the idea is you have your input x, and let's say with probability half, so this is a tree with probability half, you do one action or another action. And then from here, with probability half, you do an action or a different action, and different paths can end up to the same bit string at some point. And then the probability of this bit string is just the sum of the probability of this thing with this thing, right? And because this is probability half, this is probability half, the probability of this path is a quarter, of this path is another quarter, so the probability of this happening is a half. Okay? So it's like, it has like a sum over history type of view. And this sum over history should ring a bell to those of you that are familiar with Feynman sum over history approach. Okay? And we're going to see that in a bit. Okay, so the idea is that you start with your input, and then after a polynomial number of time steps, you end up to some output bit strings, and each of those bit strings is a yes or no. But basically, when you actually run the algorithm, you only get one of those in the first time that you run. So you kind of need to run it multiple times to get all those outcomes. Anyway, the probability of yes is just the sum of all the yes bit strings, and the probability of no is the sum of all the no bit strings. And it is in BPP if the probability, if your algorithm outputs probability yes with probability greater than 2/3 when your input is yes, and when your input is no, the probability of yes is less than 1/3. So there is a gap. So you don't guess it always correctly. If you give me input, I may fail to succeed in guessing it correctly. But I have a constant probability of guessing correctly if this bit string is a yes or no, right? And of course, if is this clear? Okay. So that's what BPP is. For now, I'm just defining the classes. I'm not saying anything about the relation of the classes. The next class is the NP, the non-deterministic polynomial. So this is the class of problems for which a solution can be verified in polynomial time by a classical computer. Let's not why it's called non-deterministic polynomial for now. I mean, but let's see what this means. So this means that it may not be possible to find the solution of a problem in polynomial time. So if you are in NP, it may or may not be possible to find the solution. That's not what defines whether a problem is in NP or not. But if one gives you a possible solution, you can check whether this is a solution or not in polynomial time efficiently. So. So for example, if you are given a witness, so if you're given, so it may not be simple to solve, a Sudoku puzzle, or it may not be easy to factor something, but if one gives you a candidate solution, you can very efficiently check, is this a solution of the Sudoku puzzle, or you can divide the big number and see it was a factor of this number or not. So these are things, I mean, dividing you can do efficiently. So these are things that you can do. So basically, if given a proof, you can check whether it is valid or not. So you want to test? Okay. Okay. So this is what the class NP is. Right? And then the final classical class that I'm going to define is the so-called P-space. P-space, so who has heard of P-space? Okay, good. So is the class of problems that the classical computer require polynomial space to solve. So basically you need polynomial memory. But you don't care about the time that it takes. So you can take arbitrarily long time to solve it, and it's still in P-space if the memory you require to solve this problem is polynomial in the input size. So this is P-space. Is this? Yeah.
Maybe a super naive question. I've never been in complexity theory. But in classical computing, there is this notion of memory time trade-off. Like you can have fast algorithm if you use, like store more memory, or you can have and vice versa. But in complexity theory, you cannot. I mean, those are classes, so you cannot, sort of try to take exponential memory when there's problem, but solve it in polynomial time. Or then maybe a trade-off. Take polynomial memory, but solve it in exponential time, vice versa. For a single problem, you cannot jump between the two. So problem is in one of the cases. You cannot do sort of this trade-off between exponential and polynomial.
So.
The question is so meaningless.
No. I'll reply. No, I'll reply. So there are trade-offs. And the trade-offs, I mean, the way you define the complex class is this way. And then if there is a trade-off, you can define, you can see whether two complex classes are the same, or the one contains the other, and so on. Now, in the particular case, what you are asking basically is whether P-space and P are the same, basically, because you're saying, okay, P, I don't say anything about the memory in P. The way I define is that I only need polynomial time. I said nothing about the memory, about the space. And here, I have P-space, I have polynomial space, but I really don't care about the time. So in a sense, what you said is P-space equal P? Actually, it's not. And I was planning to say this later when there are the relations, but maybe I can say it now because it makes sense since the question was asked. So the point is that if you have an algorithm that you have a polynomial number of steps, even if you have an exponential memory, you cannot access arbitrarily many positions in the memory. So basically, if you have a polynomial number of steps, you will always be able to access only polynomial part of your memory. Therefore, you cannot really use all your memory. And that's why there is no trade-off in this case. Actually, P is very much strictly contained in P-space. Yeah, so that's the reason. It's not trivial at all.
Storage of potential amount of memory, you will need in some form also access it, which
Exactly. Yeah. But you could have other trade-offs like milder, for example, with, yeah, or in quantum case that you, yeah. Anyway, but it's a perfectly valid question. Yeah. Thanks. I was actually planning to say that when a bit later I say about the relation of the classes and yeah. Okay, so now I'm basically done with classical complexity classes. So I'm just saying a little bit of background, and then I'm jumping on the quantum complexity classes. So the concept of complete problem. So you have a complexity class C, and you say a C complete problem is a problem that is in this class, belongs in that class, but it's basically you can use that problem, resources within another resources within the same class to solve any problem in the class. So in a sense, it's like the hardest in the class. So, you know, the toughest guy or girl in the class. So this is what a C-complete problem is. A C-hard problem is a problem that suffices to solve all the problems in that class, but it may or may not be in your class. So it may be outside your class, but still you can use that to solve all the things in the class, right? Okay. So this is the definition. But now when I said complete or hard, so I told you that if I can solve, let's say, NP-complete problem, then I can solve all problems in the class NP, right? With no more overhead that I would have from NP. But this is not the practical way to do this. Because, yes, I will, because if I use that problem, if I use, let's say, traveling salesman is an NP-complete problem. So if you use this to solve a different problem in NP, it may not be the best way to solve the first problem, because you may have an overhead. Now, the overhead may be polynomial, so it doesn't count in terms of complex theory. Who cares? I mean, it's just a polynomial, you know, this n to the 8,000. Well, it's not n to the 8,000 this time, but the point is that while solving one C-complete problem is sufficient to efficiently solve all the problems in that class, it doesn't mean that this is what you're going to use every time. So you still have lots of work to do if you really want to solve something practical. The second point to note is that relation between complex classes are typically conjecture, and they're proven subject to some assumption. What this means, there are certain cases, as the P and P space that I described to you, that you have results that prove certain relations. Especially inclusions, are easy to prove in certain cases. Strict inclusions are not so easy. So, for example, I'm going to say this in the next slide. P is included in NP. I'll explain why. But proving that P is not equal to NP is something really, really hard. It's something that everyone believes it's true, but it's something that is very hard to prove. And it's actually one of the basic assumptions that you try to prove something about two other complex classes, and you prove that this is the case unless P equals NP. And everyone will go, ah, yeah, so you proved it. Because you proved it up to a certain assumption that everyone seems, well, OK, maybe it happens that this is not the case, and then all the complex theory field of computer science collapses. But you know, that's kind of the level of things. Or it may even be that a specific problem that everyone has tried to solve in a way and no one can solve, and people really believe that this specific problem is hard. And you're saying, OK, I proved that these complexity classes are separate, are different, provided that this problem is indeed hard, as everyone has anticipated. So you'll see many conjectured relations between complex classes, but people respect them a lot. Because, you know, there's some can actually say concretely without assumptions, while there are very, very strong beliefs about this. Actually, if you wish, even the fact that quantum computing can outperform, you know, classical computing is not absolutely proven without any assumption at all.
In that case, for instance, if someone chose P equals NP, would the quantum computing field
No, because BQP is not are out of well, there are problems in BQP that are believed to be outside NP. So even if P equals NP, you're still not done. but there are certain certain problems. So for example, this thing there exists certain thing called polynomial hierarchy. There is a level of relations of classes. The very first level of this hierarchy is basically P is not equal to NP. P is contained in NP. And everyone believes that this hierarchy is distinct, that each level of this hierarchy is strictly larger than the previous level. Okay? And there are many results, actually the ones that prove the hardness of certain quantum advantage experiments that rely on the assumption that the polynomial hierarchy doesn't collapse at the third level. So that, so this is kind of a weaker version of P equals NP. So a lot of the quantum advantage experiments are based on, well, of course, proving advantage is one thing because you may not have exponential separation and still have a better quantum algorithm. But I mean, if you want theoretically to prove the advantage that you observed an advantage that comes from an exponential separation, then this is it. We're going to see a bit about this later. Yeah. I'm going to talk about quantum advantage, quantum computational advantage, and these things at the end. Okay, so let's. Yeah, right. I'm still not there with the classical complex classes. Here are the relations of the classical. So P is included in NP. Why? Because if I can verify something efficiently, well, if I can solve something efficiently, that can be my witness. So you want a witness that you actually you can verify if you see a solution, and this is actually solving the problem. So P is included in NP, and NP is included in P space because of the argument that I gave earlier. Then we also know that P is included in BPP, and BPP is included in P space. Okay, so we know these results for sure. Then there are two main conjecture relations in classical complex classes. The one is that P is not equal to NP, and we have very, very, very strong reasons to believe this. And the other might be intuitive, that actually P is equal with BPP. So adding classical randomness doesn't help you complexity theoretically. It does help you a lot practically. So, and this is not proven yet, actually. It does help you practically, so you may have a much more efficient algorithm using a probabilistic algorithm than using a deterministic algorithm. But the more efficient could be, I don't know, a quadratic speed up or whatever, like a polynomial speed up. It's not an exponential separation, generally. And so they are the same complexity class. Also, you may prove that these are not equivalent subject to an oracle. This is something strange that I'm not going to say much about here. But the fact that if you have a complex class and you give also access to this complex class to some oracle that has some extra abilities, then people believe that if two complex classes are the same, then if you give them extra access to an oracle, they should remain equal. And this is one of the indications that they are equal, because it's easier to prove that two complex classes are equivalent when they're using some oracle. But actually, you can find a separation between P and BPP if you use an oracle. But yeah, anyway, so this is the reason I didn't want to get too details in this, because it's more important to keep the general picture. I mean, just believe me that in most cases, P equals BPP. You can basically assume this complex theoretically. Now, the reason I mentioned this is because some of you might have seen Dodge-Josa algorithm. Dodge-Josa algorithm basically shows a separation between P and exact quantum polynomial line. I think I'm mentioning it later on. But, and there you have a classical probabilistic algorithm that is efficient. The catch is that you're using an oracle for Dodge-Josa algorithm. And that's why these two are not equivalent, subject to the oracle. So that's the only reason I mentioned it. In case that people know the Dodge-Josa algorithm, they're wondering, what is this guy telling us? I mean, that's what I'm telling you. But yeah, other than this, you can just believe me. Yeah. OK, we go to quantum classes. Yes, so the first everyone knows and loves this probably. This is the bounded error quantum polynomial. We'll be unemployed if this fails. Just kidding. Probably we'll find something different to do, but this is the set of problems that, well, and I'm going to tell you later that this is not all about quantum speedups, but yeah, we're just kidding. So these are the set of problems, decision problems here, that are solvable in polynomial time on a quantum computer. Now, quantum computers behave like probabilistic computers with complex value probability. So if someone asks you, I think that myself, when people ask me, so I mean, not in my field, they ask me, so what is a quantum computer? What do you tell them? You start saying about entanglement, they get lost. Well, if at least they understand the notion of probabilities, well, they will be impressed if you tell them, okay, probabilities can be complex valued. But then you can basically say, okay, I'm using this complex value probability, and then they have different properties than classical probabilities, so they enable me to do more things. So this is the way I explain what quantum computing is. But let me explain here as well how this thing works. So you have your input bit or qubit string x, and what you do is that now instead of a probabilistic algorithm, you have amplitudes, right? So when you apply a gate, you can get superposition of states, right? Now your superposition of states basically assign some amplitude in the different bit strings, right? And this is a complex value thing. So you get some amplitude, let's say +1 to go from here to here, and +1 to get from here to here. And then you do the same thing with this gate and this gate, but you can have different signs. You see minus and plus. So while classically, to reach here, you just add this probability with this probability, and this is always bigger than the single history. In the quantum case, they're adding, but they are complex values, so they can cancel. But if they cancel, then you kill the tree. You kill one leaf in the tree. So instead of going exponential, for in each layer going 2 to the number of potential outputs, you're getting some of them canceled, right? So you see, after a number of steps, this is killed, so it has no future. So and this and this. So you don't end up with all the bit strings that you would end up in a classical probabilistic algorithm. And this is a polynomial number of steps, polynomial to the input qubit. And then some of these outputs are yes, some of them are no. And to compute the probability of yes or no, what you do is that you take the sum of the amplitudes of the yes, and you take the mod square of them. And the sum of the no, and you take the mod square. And it's in BQP, if there is a, like a gap, like in BPP. So if the yes, when you have yes, is greater than 2/3, and the no, and when the answer is no, it's less than 1/3. So you have a gap between these two. And you can see, because you take this sum, you have some paths killed. So you see, to actually get a speed up, you need an algorithm that you have the terms that end at 2, or generally the leaves canceling each other. So it's a non-trivial thing. So you need quantum algorithm design. So you need to be smart to get a speed up. Yes, you can generate equals. If you think of all the algorithms you generate a quantum superposition, but you don't measure after you generate the superposition. You do things. Now the things you do is that you mix the different branches in a way that cancel each other. So at the end, you get the desired outcome, well, amplified in the case of Grover, or completely, and so on. So this is the concept of what happens in quantum computation. So if you take the sum of the amplitudes, you have the diagonal terms and the off-diagonal terms. Now, the diagonal terms behave like classical probabilities, just the sum of each of the histories, right? But this one, the off-diagonals, is the interference. So this is the interference. And this interference can completely cancel that probability, or it can double that probability, and so on. So it can amplify or cancel. Now, in classical systems, what you have is that the amplitudes, the different amplitudes you have are random. So this means that the interference, on average, is 0, or, well, it's much, much smaller in order than this thing. Okay? So if they are completely random phases, then these are, much smaller than this term. So you are practically only having these terms. Okay? And examples in BQP are like factoring, source algorithm, or quantum circuit simulation and so on. Again, factoring made to a decision problem, as I mentioned earlier. Any questions so far? Okay, so I'm done for now for BQP. I'm going to say relations about BQP later, but I'm done for now. And the final complexity class I'm going to define is the QMA. How many of you have heard of QMA? Okay, fewer, but still, good, yeah. So I hope that there were new things for all of you here, but yeah. So quantum MA is quantum Merlin-Arthur, so you know the myth with Merlin and Arthur and so on. So basically, yeah, I'm not going to say the history of it, but just the definition. So it's a class of problem for which a solution can be verified in polynomial time by a quantum computer. Okay, so it's basically, you can give, you have Merlin that gives a proof, which is a polynomial-sized quantum state, to Arthur, and Arthur can take this polynomial-sized quantum state and run a polynomial time quantum computation and decide, was this a solution or not? Is this a yes instance or not? So that's the idea. And basically, QMA is to BQP what NP is to P. So this is the, efficient verification of what you can efficiently, the same way that NP is to P. Well, strictly, MA is like, and MA is to BPP, what NP is to P. And yeah, so this is missing here. Sorry?
How is poly-sized quantum state defined?
Well, first of all, you need to have a polynomial number of qubits, basically.
I see. So you need the number of
To the size, to the access, to the input size. Yeah, it needs to be polynomial. So you cannot be given an exponential. An example that is QMA complete, so it's the hardest QMA problem, so to speak, is the K local Hamiltonian. So now, does this sound strange to you? K local Hamiltonian, I told you that this is what adiabatic quantum computing can solve, so there must be a catch. I'm going to come to this later. Yeah, so I'm going to say more things about K local Hamiltonian and why there isn't a contradiction here. But anyway, this is a typical QMA complete problem, basically, the K local Hamiltonian problem. But I'm going to say why this doesn't contradict anything you've heard so far. OK. And here is this picture, the simplest complexity classes relation and conjecture relation. So these are not only. So we have P space, BQP, NP, and P. Okay, so we have this thing. So what is really, really known is that, I don't have BPP here, but what we know is that BPP is contained in BQP, but not strictly. We don't know that so we don't know that there are problems outside, well, we don't know for sure. We don't have it's only conjecture that there are such problems. But we do know that BPP is included in BQP and BQP is included in P space. So these two relations we know for sure. And we do know that NP is contained in QMA. We know BQP is contained in QMA and QMA in P space. So we basically, these are relations that we know for sure. BQP being contained in QMA the same way that P is contained in NP. QMA and P space, we're going to see why this is the case. Right. So in this picture, if I had QMA would sit basically around this, but in P space. So P space and QMA are not known whether they are believed to not be equal. Okay. But it's not so relevant. Okay, so that's the relations that are known. And I'm going to say something about the implication, for example, of this thing and this thing in terms of, later on. And the major conjecture relations that you can see in this diagram are those two. NP is not contained in BQP. Right, so there are NP problems that are outside BQP. But also BQP is not included in NP. So we have these two things. These two are not proven, but are believed to be the case. I mean, they're very strong. Complex theoretically, we kind of believe that this is the case. And both of these have very important implications, what these two mean. So first, there are problems here in NP that cannot be solved by quantum computer efficiently. This means that quantum computing cannot solve an NP-complete problem efficiently. So if you, have you heard, and this contradicts things that you've heard. So, I'm sure that people say you can solve traveling salesman using quantum computing. Well, if by solving you mean efficiently, no, you can't, because it's an NP-complete problem. And that's for sure not the case. You cannot solve it. It sits there. Does this mean that you cannot get any advantage in an NP-complete problem? You can. It's just that you don't have a polynomial time algorithm. So I'm going to come to this later. So you may still be able to have a quantum advantage or quantum speed up compared to a classical solution. So it's not pointless to ask this question. But if you're really asking, I want a polynomial time quantum algorithm, no, you can't have that. Or if you have, you're good to get, I don't know, a big prize in computer science if you prove that. Yeah. So that's one thing, the first implication. The second implication that there are problems here that you cannot solve efficiently is that you can have public key classical cryptography that is secure against quantum attacks. Okay? And this is really important. So when people say QKD, okay, we need QKD because when you have quantum computers, you're going to break public key cryptography. No, you're not going to break public key cryptography. You are going to break public key cryptography that is based on factoring, yes, because factoring is one of those problems that are here, are in NP, outside P, but in BQP. So factoring is here, okay? But there are problems here that are perfectly well suited for a public key crypto system that is secure against quantum attacks. And there are a number of candidates for this, like lattice-based cryptography, code-based cryptography, that are basing the security of these algorithms on problems that you don't have. You almost certainly know that there is no efficient quantum algorithm solving them. Well, the catch is that those problems may not be as practical as factoring or discrete logarithm for classical crypto systems. And there are also the issue that maybe you don't know that well what's the best quantum algorithm. Okay, you don't have an efficient algorithm, but what about which is, in order to use a quantum algorithm for cryptography, for everyday cryptography, you need not only to know that there is no polynomial time solution, but you need to know how big you need to set your input to be certain that you're not going to break it. Now, how big doesn't depend only asymptotically on things. It depends on concrete values. So which is the best actual algorithm? So a very interesting question is, what speed up? Well, you're not going to get an efficient algorithm, but what speed up you can get to those problems that people are using for quantum safe public key cryptography using quantum computers. This is one field I've been working also. So when Alfredo said that I don't work in quantum cryptography but not QKD, well, this is one of the examples of the things I've been doing. Some quantum algorithms trying to attack these type of problems, not to break them, because I know I'm not going to break them, unlike other people, but to make the best quantum algorithm for those. Okay, right. So the second side, BQP is not in NP. So there are problems in BQP that are outside NP. Well, first of all, this means that because NP contains P, this means that there are problems in BQP that are outside P. This is good news because it means that we can have quantum speed up. Okay, good. But the second thing is there are problems that, other than those problems like factoring that are outside P, but you can verify them efficiently, there are problems here, right? And what does this mean? Is there are problems that I can find a solution using a quantum computer, but I cannot test whether my solution is correct or not. So there is a big question of how to verify a general BQP complete or a problem in BQP that is outside NP quantum computation. So you cannot do it classically, but there are a number of approaches. There's a big field called verification of quantum computation that has two aspects of this. The one is the practical verification, benchmarking, testing. But then there is the theoretical one to actually, that touches how you can even, access this side and confirm that the solution is correct. Because imagine you build this really, really expensive quantum computer, and you want to find something about, materials. And, once you find something about materials, then you need to devise a very, very expensive experiments using those things. And everything relies on this black box spitting an answer that you have no idea whether it's actually correct or not. I mean, you can have an idea of whether it was computed as it's supposed to be computed, but because you say, okay, the fidelity is high, but do you actually know that is the correct solution? It might not be clear. Also, do you know if a company tries to trick you, and gives you a solution? How can you check that the solution that the company gave you is actually the correct? Anyway, so this is a big challenge. It's a field. There is a lot of research and very interesting results in this field. So it's just, yeah.
Can you name an example problem that is believed to be in EQT but not in?
Well, actually, some of the sampling problems that we're talking, so are there actually, and there is a big, discussion in the quantum advantage problems how to confirm that that advantage has been achieved, because you also, So this is one example. Also, simulation of quantum systems should be there as well. I mean, in many cases,
Yeah, maybe that quantum advantage paper by Google from 2019 was a good example of probably a BQP, where they basically say, okay, we sampled from this unitary, here is the distribution, but you're free to check whether it's correct or not.
Yeah. No, and one thing is that, if I remember correctly, I mean, in certain cases, when you are just in the boundary of quantum advantage or not, there are things that you could do once off, in a sense, and you can kind of confirm. But, but even those things, they would be completely impossible if you go to, I don't know, 100, 200 qubits. So yeah. Anyway, but it's a very interesting field. So there are protocols that use so QMA, for example, says that you can have a quantum witness, right? So maybe you can do the computation in a way that it also outputs some quantum states that provides a proof that what you did is correct, in a sense. So there are these type of approaches, for example. And I know, for example, for boson sampling, there are some papers on how to verify boson sampling. But yeah, anyway, but I only mentioned here that one of the basic implications of this diagram is that there is this whole very interesting and fruitful field and with this important challenge. Okay, so now I'm going back to the K-local Hamiltonian problem and back to the models of computation. So I want to define what this K-local Hamiltonian problem is. So it is to find the ground state of a Hamiltonian that is a sum of other Hamiltonians. And the number of terms you have in the sum is polynomial in your input. And each of those terms acts on at most k qubits. Okay? Now, k can be small number, it can be 2, 3. Actually, we'll see that even two local Hamiltonian is good enough. Again, now you've been warned about this. So when I say local, I don't mean local like physical local. I mean local, that it involves 2 qubits. These 2 qubits can be in the other end of the, device, or even the universe. For me, I don't care. So yeah, so you've been warned about that. So that's what I mean, a k-local Hamiltonian. This type of problem is the main problem in adiabatic quantum computing, in quantum annealing, in variation quantum algorithms. So it's the main problem in a big area of, in a good number of models of computation. Now, the crucial thing for this that quantifies what can and cannot be done is the so-called spectral gap. So this spectral gap is the difference in energy in the ground state and the first excited state. Okay, so you have the energy of the ground state and the first excited state, and the spectral gap is how far those two are. Now, if the gap is bigger than 1 over a polynomial, then you can prove that you can achieve adiabaticity in polynomial time. So how slow you need to evolve in adiabatic quantum computing or Hamiltonian to achieve, to remain in the ground state depends on the ground state, on the spectral gap. And the gap needs to be 1 over polynomial in order for a problem to be solved with adiabatic quantum computing. And if it can be solved in adiabatic quantum computing in polynomial time, then it can also be solved in BQP, basically. You can prove that you can also construct a circuit. So you can prove that if you have adiabatic quantum computing with polynomial running time, adiabatic quantum computing, you can have exponential running time, but this is not going to be in BQP. This is not an efficient model of computation. So you want to restrict to adiabatic quantum computing that runs for polynomial time. So if you want it to run for polynomial time, then this model of computation is equivalent with the circuit model. Why? Because if you give me a circuit, I can turn it to a Hamiltonian that has a gap of this type. And if you give me a Hamiltonian with this type of gap, I can find a circuit that gives the solution, a polynomial size circuit that gives the solution. So these two models are equivalent. Again, when I say equivalent, I mean in complex theory. It doesn't mean that they're equally practical, the mapping. And specifically, the mapping is never the way to go through. I mean, I'm going to say more about this in a minute. Anyway, so we can turn any polynomial size quantum circuit to K-local Hamiltonian that has this type of gap. Now, the catch was, OK, I'm just saying this here. Oh, great. Yeah, OK, I should know better what's in my slides, so I move to the slides that I'm talking about. Yeah. Yes, so this generic map that's used for this equivalence between adiabatic and circuit is not practical. So you can have the same problem, and you can solve it with different Hamiltonians. OK? So, for example, if you take Grover algorithm, search algorithm, and you just do the generic equivalence between adiabatic and between circuit and adiabatic, or you do some naive, like approach, then you end up losing the speed up. Why? Because the Grover speed up is not exponential; it's a quadratic speed up, so it's a polynomial. So losing this polynomial, it's a polynomial overhead. But in this case, when your speed up is polynomial, it's kind of important if you lose it. But on the other hand, you can recover in adiabatic quantum computing the search speed up by performing adiabatic quantum computing a bit in a smarter way. So anyway, this is possible. So the moral here is that when you try to solve a problem in adiabatic quantum computing, you need to think afresh. You shouldn't, I mean, well, you can try what people have done in the circuit, but you need to think fresh how to solve it in adiabatic quantum computing. And what you know about the circuit, it will help you knowing about exponential separations and so on, but not about practical speed ups. OK, so now I'm coming to this. Actually, even k equals to the 2 local Hamiltonian is QMA complete. And here is the catch. It's QMA complete if you allow for a negligible gap. So if you allow for a gap that is even smaller than 1 over a polynomial. So if you have a gap that is 1 over an exponential, it's really, really small, then it's QMA complete. But of course, if you wanted to do this with adiabatic evolution, to ensure that you don't jump, if there is really the gap, you need exponential time to evolve it, and then it will no longer be a polynomial time algorithm. So yeah, so that's the cut. So is this clear? Does this solve the earlier question? OK. An interesting thing is that, so even if I have a Hamiltonian that has negligible gap, I can still use the Hamiltonian as a heuristic to run VQE or things like this. And I can use it to try to solve a problem that is outside BQP. Of course, I don't expect that I will have high probability of success, or at least not high probability of success for a general case. I mean, when you have a complex class, you have instances that may be simple to solve and instances that are hard to solve. So when you say that this problem is NP-complete, you can still have an NP solver that solves some instances of the problem, but it fails, your solver fails in some other cases. So you can actually do the same thing because you have this Hamiltonian. If you give me this Hamiltonian, I can run VQE. If the gap is negligible, however, if I run VQE, the probability of actually reaching a good approximation of the ground state will decay exponential with the size of the instances, but it would still give me some non-zero probability. And it may actually, for instances not too large, that this exponential completely kills the probability, may still be relevant. So for practical applications, it's something, an attempt that one could make, but needs to be very wary of what they're doing. Okay, yes, I can run it. Yes, I can try to solve things that I'm not supposed to solve efficiently in a quantum computer, but I should know the limitation, and I should know not to expect to find a general solution here. Okay? Right, so this is about the K-local Hamiltonian. And now some implication about classical emulation. Now, classical emulation, I'm using this term for basically simulating a quantum system classically. So that's classical emulation, what people are using. Yeah. So we have some complexity results that have implication about this. The first one is that BQP is included in P space. So this means if I don't care about the time that my algorithm takes, I can have a classical algorithm that simulates my quantum computing, right? So if I don't care, well, you know that, because practically you just take the matrix and multiply them. But this result basically tells you that if I don't care about the time that my algorithm runs, I can surely simulate with a classical computer that has polynomial size the quantum circuit. Okay? The second thing is that if there are problems that we have quantum advantage, so if there are problems in BQP and outside BPP, which is implied by these, then a classical simulation of general quantum computation cannot be done efficiently in polynomial time, and this is the whole point that we're, well, it's not the whole point, because you can have other advantages as well, but this is the main, exponential promise of quantum computation, basically. So what about classical emulation? So one can have naive classical simulation, but this is really, really impractical because it's exponential. So because what you need to keep is you need to keep track of like the naive emulation that you just multiply the matrix. You have your state vector is of exponential size, and you actually need to keep the full state vector. So this is really, really impractical. But this is not the best way to simulate a quantum system, as you know. So, for example, if you have, for specific class of circuits, you can use, you can even classically do an efficient classical simulation. So, I'm sure most of you have heard of Goresman and Neal theorem, or if not in this name, you must have heard that if you have Clifford circuits, then you can efficiently classically simulate them. So the idea here is with the stabilizer states. So instead of representing your state vector as, a vector, a bit string with, well, superposition of bit strings of that you have 2 to the n different this, and you just keep 2 to the n amplitudes. Instead of doing that, you define your initial state with respect to the stabilizers of that state. Okay, and these are, like polynomial, actually are linear in the size, in the number of qubits. And then whenever you have, for each gate, the property of Clifford gates are that they take Paulis to Paulis. So if you start with a Pauli, and when you apply a gate, what you do is you just update, you change the stabilizer of your state. So instead of keeping track of the amplitudes, you keep track of the stabilizer of your state, right? And then you just have polynomial number of steps to do this, and you can simulate this classically. Okay. Of course, this is a restricted version. But you can do better than naive, of course, as you know, for general quantum computing circuits. So for example, this Bravi and Gosset emulator, that you have a circuit that has Clifford, and the only non-Clifford gate is T gate, which is sufficient for universal quantum computation. And then this algorithm uses this stabilizer formulas and certain approximations, and it goes exponential not in the number of gates or in the number of qubits, but it goes exponential in the number of T gates, and this is much better. You can run much better algorithms. And then there are tensor network techniques as well. The final thing on classical emulation I want to say is something interesting. Noise could actually help. So if you take the naive approach, if I have a noisy system, what do? I do the usual gate, and then I apply a noise channel with it. But this is actually harder than doing the noiseless case when I try to classically simulate things, right? But intuitively, if you add noise to a system, it shouldn't be harder. It should be to classically simulate it. It should be simpler. Just take the limit that you take many, completely random. You have very much noise and your output's random. Well, you don't need to simulate the quantum circuit. You just toss classical coins and you get your outcome, right? So intuitively, the noise should help you, but should help you if you're using a more involved technique. So you don't try to sample from an exact distribution. You try to sample from an approximate distribution. And even complex theoretically, you can prove that sampling from an exact distribution is harder than sampling from an approximate, from a noisy version of the same distribution, actually. Yeah, there are known results, actually, that for certain types of noise, you can actually you exploit that. Now, for quantum computational advantage, we definitely need to beat the best classical emulation. Why? Because, of course, with classical emulation, you don't need the quantum device. But, of course, this is necessary, but it's not sufficient. Because one can try to solve the same problem with a completely classical algorithm that doesn't even mimic your quantum algorithm. So when you say that I have a quantum advantage, you shouldn't benchmark against classical approaches to mimicking your quantum algorithm or similar approaches. You should benchmark against any possible classical algorithm, and this is a hard thing to do. Yeah, basically this is something that is hard and something that is basically moves also because it changes what is the best algorithm. So some claims, if you remember exactly the Google result, and a few days later IBM said, well, not quite. I mean, we cannot quite do it classically, but we can do it in a few days instead of hundreds of years, and this type of things. Right. Okay. I think I'll finish with some things about quantum computational advantage. So, actually, no. Yeah. How much time do I have?
20 minutes.
Okay. Fine. I was under the impression I finished at 5:30. No, that's fine. Yeah. Good. Okay, so I have a few more things, and that's fine. I have time to tell them, and have time for discussion as well. So the problem is demonstrate that the problem can be solved using existing controllable quantum hardware. Controllable, so it's not a completely fixed, thing that is infeasible classically. And of course, these words need, specification, what infeasible means, and so on. Before that, just what I call quantum computational advantage. Of course, you have heard that they use the quantum supremacy, quantum computational supremacy, quantum advantage, and so on. I prefer this for whatever reasons. But, it's the same thing, basically. So the first thing to see is nowhere in the definition of this there is anything saying about what the problem can be. So it can be a completely useless thing, a completely useless problem, or a completely designed problem designed to be well-suited for a quantum device. So in that sense, while it's a huge milestone, actually, to achieve this, and it was, really impressive result, historic, I would say, it's not the end of the story. It's like the milestone starting the discussion of quantum advantages, because that's, it's not really of practical relevance. So what you need is that you need a quantum solution that is reliable in noisy quantum device. So the quantum solution should run in these noisy devices. The problem that you're considering has guarantees that is asymptotically hard classically. So you need some, exactly because if you don't have, roughly speaking, if it's not a problem that you have reasons to believe that there is an exponential separation. So if you believe that there is an exponential separation, even if someone comes up with a better classical algorithm and says, okay, it's not 1,000,000 years, it's just 2 years, okay, you add 3 qubits and you are back to 1,000,000 years, or well, you add 10 qubits and you're back to 1,000,000 years if there's an exponential separation in your problem. And okay, you didn't quite did it, but you're close on in doing it. If the problem that you're trying to solve doesn't have an exponential separation, finding a better classical algorithm could be the end of, the end of the claim of advantage, so to speak. So this, I mean, typically they consider this thing. Of course, achieving advantage even in other problems that you don't have asymptotic guarantees is still a very interesting fit, but it's not, when people say quantum computational advantage or quantum computational supremacy, they typically mean problems that have this thing. And then some proof or indication that existing quantum hardware significantly outperform best classical algorithms on classical hardware. Of course, what significantly is, a bit relative. Okay, 1,000,000 years, yes, but a few days, still it's outperforming. But yeah, I mean, so these are matter of interpretation. The first thing to say is that best classical solution is a moving target, as we've seen in practice. But if you have the asymptotic guarantees, it's a moving target that is not going, it's a moving target as long as we are in the same order of magnitude of qubits. Now, if from 50 or 60 or 70 qubits, suddenly you go to 200 qubits, that's the end of the story. If we are talking about, even few more qubits, it's the end of the story. The other thing is that already noisy emulation raises concern in some cases. So for boson sampling, not for Gaussian boson sampling, for boson sampling, there are results if you have, so in boson sampling, you assume that you have indistinguishable photons, and you also assume that you don't have losses. A real system, you have photons losses, and you have photons that are not completely indistinguishable. Now, if you require, I don't know, 70 photons or 50 photons to reach that's in boson sampling, even if there is a small distinguishability between the photons, then this 50 grows a lot. And there are some results that demonstrate that. So again, the target moves a lot, so to speak. And of course, this is one question whether such taking these ideas from boson sampling can also be done in Gaussian boson sampling that would put to question some of the supremacy, quantum advantage claims. Now, the candidates are all sampling problems that are outside BPP, proven to be outside BPP. So random circuits, sampling from random circuits, which is what Google did. Boson sampling, Gaussian boson sampling, which is what people did, the other advantage experiment in China. And IQP, so IQP is instantaneous quantum polynomial time. So this is another complex class I didn't define. So it's basically a complex class that consists of commuting gates. So your gates are commuting with each other. So this practically means that you have a circuit that you can kind of do all the gates simultaneously, more or less. So, and that's why you have bounded depth in your computation, and this is a limited version of BQP, so it's not universal, this type of problems, but one can prove that it has to be outside BPP unless polynomial hierarchy collapses in the third level. You'll be hearing this song a lot, the polynomial hierarchy collapsing in the third level. Actually, I think Scott Aronson wrote a joke newsletter like, you should look at this about breaking news, the polynomial hierarchy collapsed in the third level, and so it's a very funny letter. I advise you to see. I should have found it. Yeah. Anyway, yes, and there are survivors. Complex classes survive the collapse and so on. Anyway, which are the implications that didn't collapse? This one is not. Anyway, so the claims that this quantum advantage has been achieved is with superconducting qubits with these random circuits and photonic with this Gaussian boson sampling. And in all those cases, the challenging question is how to verify this quantum advantage. We discussed this already. Now, while this is an important milestone and very interesting question and still has many things to demonstrate, the fact that the problem is not relevant and the requirement that the problem has asymptotic exponential separation leaves some more questions. So this is not all we want to do, basically. So there are many things that we want to do that is not captured by this. And this is what about other types of quantum speedups. So I'm going to say a few words on this and finish after that. So the first question is, are only the problems that we have a quantum speedups in BQP but outside BPP? So is this the only type of problems we care about? No, that's not the case. We can have smaller but practical speedups. Already we know that Grover speedup gives a quadratic speedup, which is very generic speedup, and it's really important in practical terms, but is not there because it's basically outside BQP. I mean, the Grover algorithm runs in exponential, so exponential time. So if your database has n elements, it means that you can describe it with 2 to the n, which is your input size is n, right? Small n, the exponent. So basically, Grover algorithm is an exponential algorithm. So if you have a database with exponential many elements, searching in that will take exponential time. And the quantum speedup is just give you a square root advantage to that. But it's extremely relevant for many applications. Another thing is that so this is not captured by these problems because it's outside BQP. Another example is that we can have steps for an efficient task. So let's say that you have something that can be solved classically in linear time. So this is in P, well, or in BPP, whatever. So it's not outside BPP. But if you use a quantum algorithm, you can solve it even more efficiently, logarithmic. So this is HSL, for example. So this is algorithm that is not of this type. Here you have exponential separation, but it's not between polynomial and exponential. It's between polynomial and logarithmic. And even there is this shallow circuit result that the classical complexity to solve this type of problems is logarithmic, while quantumly you can solve it in constant depth. So there are this type of separation. You can also have oracle separations, as we discussed, Dodge-Jozo. Okay, and then the second question is, can we find useful speedup? So this is maybe even the most crucial question, at least for the near-term future of our field in terms of interest and applications. I firmly believe that quantum computing is the answer for the future, even if we fail to find near-term applications, which we are likely to succeed. But even if this fails, I imagine that in the far future, we're not going to talk about computer science. It will be quantum computer science. But having said that, for now, for the field to progress right now, we need applications now-ish, like in the near term. So let's turn it around. Give me a problem or a particular use case, and let's try to find the best quantum algorithm, and that the best quantum algorithm give any speedup. I don't care about exponential speedup here. I care about any speedup. And I may not be able to get speed up with existing hardware, but if not, can you tell me what should I expect? So how many qubits and what quality of qubits should I wait in order to get my speed up? So basically, like you have a person that comes with a problem, that has no idea about quantum computing, and comes to you. And what your task is in here is that find the best quantum algorithm and do, a detection of and you can basically tell them, okay, you will need to wait till I have this number of qubits and this quality, and then you'll get this type of speed up. This is really important because this will bring, to real terms where we are, I mean, how far we are in its application, and will make us also focus on the correct application, not in any application in a sense. So this is an important, very important question in the field. And this best algorithm can be different models of quantum computation. So one should be open, should be knowledgeable, because different models of quantum computation may give you advantage for different problems, or even heuristics. One making this study, understanding what's the best approach, would require to have a good knowledge of all these fields, and in order to really determine that. So this is and also hardware, because you need to have an overall idea. And in that case, actually, the advantage to existing classical algorithms suffice. I don't need to prove that there is no, that there's an asymptotic separation, and I don't even need to prove that there is no other classical algorithm. Well, I give you a quantum algorithm that can beat your classical algorithm. If in 5 years you come with a classical algorithm that somehow is quantum inspired or not, but beats my algorithm, that's fine, that's life. You know, like in classical algorithms, that's what you do all the time. So you have a classical algorithm which is superseded by another classical algorithm. So given that in the future we will have quantum, finding a quantum solution that right now is the best existing solution is absolutely sufficient, even if at some other point someone finds a classical solution to the same problem. And this is in terms of practical applications, this is the type of question that one needs to answer. Without me wanting to, you know, undermine at all the quantum computational advantage milestone, which is huge and it's a very important question, at least from an outwards looking perspective, this type of question is the thing that one should focus. And it has a lot of understanding of quantum algorithms and quantum hardware to actually be able to do this deduction, because there are many different approaches, and in each of those approaches, many optimized versions of running those algorithms. So I think I'll stop here, and yeah, thanks.